Good evening, all the participants and resource person, Vinod Kumar sir. We welcome you, sir, and it's my honor to introduce our first today's resource person, Vinod Kumar Notaki. He completed his MTech in cryogenic engineering from IIT Kharagpur, and he is a founder and managing director for Jesuit Cryo Technologies Private Limited. And sir has total experience of 14 plus years, and his skill sets are in design and development of mechanical static equipment, liquid hydrogen storage tank, liquid hydrogen heat exchangers, PAM electrolyzers, solid oxide fuel cell, hydrogen fuel stations, hydrogen distribution, fuel cells, hydrogen transportation, liquid hydrogen piping, hydrogen generation by steam methane reforming, cryogenic tanks, cryo cylinders, LNG skid mounted fuel station, LCNG skill mounted fuel station, low pressure vaporizer, high pressure vaporizers, LNG semi trailers, feed booster compressor plants, API storage tanks, shell and tube heat exchangers, LNG liquefaction plants, hydrogen liquefaction plants, cryogenic recycling plant, refrigeration systems, steel manufacturing plant, vacuum jacketed piping, chemical skids, CO2 liquefaction plants, pressure vessels, cryogenic pressure vessels, vertical pressure vessels, horizontal vessels, transportable tanks, rigid tanks, trailers, heat exchangers, cryogenic atmospheric vaporizers, review of drawings, material selections, product design calculation, CO2 tanks, ISO tanks, IMO tanks, life science equipment, pressure building unit, vacuum insulated pipelines, PED vessels, TPED vessels, Bionet join, CO2 refrigeration trucks, DOT trucks, expansion bellows, new product developments, product cost optimizations. And welcoming you, sir. Now it's my request, our resource person, to take over the session.
Yeah, thank you, Anandal. Myself is Vinod Kumar, and thank you, ma'am, for introducing me in this meeting. I am the founder of Jesuit Cryo Technologies Private Limited, and our company got established 4 years before. And I have been working in various new advanced technologies in terms of cryogenics, green hydrogen, green ammonia, ethanol, e-methanol plants, ethanol plants, biogas plants, like that. Coming to this session, we are dedicatedly going to talk about hydrogen generation systems, which is the current demand in the global market. Since a lot of the companies working towards reduction of greenhouse gases emission. So on this part, we would like to talk about hydrogen generation systems, which are with water electrolysis. We have worked on various hydrogen generation methods, but we would like to stick to the water electrolysis hydrogen generation technology. In this regard, we worked on various projects with the BPCL and NTPC and other abroad companies on this water electrolysis hydrogen technology. And some of the our engineers involved in this project, who has worked directly in this hydrogen generation system, Mr. Harshavardhan, he is our senior engineer. I guided Harshavardhan to talk in this presentation with respect to this hydrogen generation technologies. I would give this time to Harshavardhan, and he will speak, and I will be there here.
Good evening, one and all. I'm Harsha, working as a project engineer at Jesuit Cryo Technologies. Under this guidance of Vinod sir, we have worked on various hydrogen technologies in completely on hydrogen value chain, starting from hydrogen generation, compression, storage, and dispensing. We work on not only the water electrolysis, but various hydrogen generation methods. So today I am here to share my knowledge on hydrogen generation. I will take into my presentation. So here, as I mentioned, I come from Jesuit Cryo Technologies Private Limited, and I want to share my knowledge on hydrogen generation methods. I hope my screen is visible to everyone.
Yes, sir, it is visible, but make it maximum, sir. Full screen.
Yes, sir. I have made it to full screen. Is it coming full screen, sir?
No, sir.
Let me share again. I hope now you can see my full screen, sir.
Yes, sir. Yes, sir. Sir, click on hide button at the bottom.
Okay.
Okay, sir.
Yes, sir. As we know all about hydrogen, just I want to walk through on hydrogen basic. Like hydrogen is we all know as it is a colorless and odorless flammable gases. But the hydrogen in the early chemistry is used for making of water. So the hydrogen is derived from a Greek word called maker of water. So from here, why we are choosing only hydrogen? Just I want to give some inputs on why we are choosing the hydrogen as a fuel. Hydrogen is having a higher calorific value, which is when compared to the other petroleum gases, it is 3 times higher than the other gases, which is 143 megajoule per kg. That means if you are burning 1 kg of hydrogen, you are able to get 143 megajoule of energy. So this is the main reason all we are looking about towards this hydrogen as a fuel. The basic things for a good fuel is higher calorific value, ignition temperature, which is already hydrogen is having. So hydrogen is considered as a good fuel compared to other petroleum gases. And the hydrogen is a carbon free and clean. Hydrogen is carbon free. That doesn't mean that during the generation of hydrogen, carbon is not produced. Carbon is produced, but it can be stored or separated from the generated hydrogen. So that is the reason hydrogen is carbon free and is clean. Using some other generation methods, we can produce clean hydrogen also. So the hydrogen is available, abundance, and the availability is abundance in this earth. Hydrogen is not easily available, but the amount of hydrogen is abundant. That means how you make, how you are separating this hydrogen as per your requirement is the challenge. And hydrogen plays a major role in decarbonization. Like we have seen everywhere that all the industries are using hydrogen for reducing the greenhouse gases. Then there are different types of hydrogen. That means the color code of hydrogen. Like as I mentioned, hydrogen is a colorless. The color code doesn't mean that hydrogen is having this type of color, but using the generation method and the type of generation method determines the color of the hydrogen. And storing the hydrogen and transportation is one of the place where hydrogen is being mostly used. Using hydrogen, we are having energy independence and security. That means the hydrogen can be produced everywhere, so that we cannot. There is no need of relying on other countries or other people for providing the technology. As we see, the water electrolyzer technology we can make everywhere, because the water is available here itself. If you see other refining where this crude oil or maybe other refineries are importing the crude oil from the other countries, so we can be energy independent. So that if we are able to generate the more hydrogen, or if we are able to make the hydrogen production methods as more and locally available, our future generation need not be depend or rely on other countries. So here hydrogen is a very energy independence. And the sustainability of the future, as we are stating that hydrogen will give the will do the decarbonization or makes this earth carbon neutral. This means this is the sustainability of the future. If we see the use of hydrogen or the applications of hydrogen, we all know that hydrogen is used only in the transportation sector or some refineries. But various sectors and various industries are using hydrogen mainly confining to the refineries. If you see, refineries are the largest producers of hydrogen once upon a time, but now due to the decarbonization motive, they are the largest consumers of the hydrogen for making this product decarbonizing. And if you see in the refineries, mainly oil refineries, we are using hydrogen for dehydrogenation or denitrogenation, where this hydrogen is mixed along with sulfur and this is separated. Only the pure petroleum gases are being produced. And in industries like chemical industries, we are generating ammonia. As per the records, in next 30 years, the ammonia consumption is going to increase 40%. At present, 1.8% of carbon is being generated on the ammonia. So here is an area by using Haber-Bosch process, that is the latest technology where hydrogen can be mixed with nitrogen, which is generated using air separation, can reduce the carbon. So hydrogen along with nitrogen gives the ammonia, which is not generating any carbon. Next, if we go to the steel industries, steel industry in the making of the steel requires high temperature, and this high temperature is obtained by using coal. While burning the coal, there is a high temperature which makes the steel, and but also the steel making process leaves the carbon out. So if we are replacing the coal with hydrogen, the high temperature is achieved as this have a higher calorific value, and also there is no carbon. And if you go for another chemical industry, that is a methanol plant, hydrogen is combined along with carbon monoxide to form methanol. If this hydrogen is being generated using the renewable electricity, then it is called green hydrogen, which this green hydrogen is used to generate methanol is called e-methanol. This is a very new emerging technology which we are working on, this e-methanol, which the e-methanol can be a fuel source to the ships and other places. And if we go for a semiconductor in the industries, hydrogen is using for silicon passivation in the semiconductor industries, and in the food industries, hydrogen is used to unsaturate the fats and oils for the preservation along with the use of catalyst. So there are different industries using this hydrogen. In the cement industries, hydrogen is also used at the burners to reduce the greenhouse gas emissions. If you see the space application, hydrogen is being used in the space application from the long back, which they are using also in the rocket propulsion and along with the fuel cells also for power generation. And if you see the power generation, that is power industry, where this hydrogen is being used to generate power along with steam. And the widely known transportation sector is having the big name of hydrogen usage in fuel cells, but having at present there is a nominal usage in this transportation sector. More number of hydrogen refilling stations are going to come up for the transportation sector, for the increase of hydrogen demand in the transportation sector. Hydrogen is being used in a hydrogen fuel cell along with oxygen, which can generate electricity, which is used to propel the car. So this is in the world at present, all are looking for this hydrogen car for the greenhouse gas reduction of greenhouse gas emissions. If you see the supply and demand of hydrogen, so 90 metric tons of hydrogen is having global demand. So global demand in all areas, 90 metric tons of hydrogen is required. So this hydrogen is being produced from different sources such as natural gas, coal, fossil fuels, oils, and other byproducts. So in this, if you see here, 59% from natural gas is being produced. This is not actually the green hydrogen or other hydrogen, but the hydrogen is being produced from the natural gas, and which has a carbon content also. So likewise, 19% from coal, 0.7% from fossil fuels, 0.6% from oils, and 21% from H2 byproducts. The gases which are being produced from the hydrogen which is being produced from the natural gas or coal having some byproducts. These byproducts also contain some hydrogen, and this hydrogen is coming at around 21%. So this is the supply of the 90 metric ton of global demand as per all the fossil fuels and renewable energy sources. From this generated 90 metric ton is being used at 37.18 metric ton is purely used in the refineries. So here if you see 59% of hydrogen is being coming mostly from the natural gas refineries, and again 37.18 metric ton is going to the refineries for the hydro desulfurization process and various processes to reduce the carbon emissions. And if you see in the other industries, as I mentioned, the chemical industries and iron industries, 46 metric ton of hydrogen is being used in these chemical industries. In that 75% of ammonia synthesis and 25% of methanol production. As I mentioned, hydrogen and nitrogen is being used for the production of ammonia, where the hydrogen is being consumed, and hydrogen and carbon monoxide is used for the production of methanol, where here also the hydrogen is being consumed. So there is a lot of consumption in this chemical industry. Along with this, it is for also consumed at the steel making process, where I have mentioned 53% of 5.3 metric ton of hydrogen is being used at the steel industry making, and the remaining 1.52 metric ton is used as the other areas where I have mentioned, such as transportation and other things. So we can see here the total supply and demand of the hydrogen. In the earlier slide, we have seen that hydrogen is being generated from natural gas, oil, coal, about this much percent and this much percent. But how this has been, production methods has been categorized. The production method has been categorized in different ways, in which let us see the processes were there. In this process, reforming, partial oxidation, and autothermal reforming, there are some of the process listed here which generate the hydrogen. So if you read this slide, the hydrogen generated using reforming process having a feedstock of natural gas, that feedstock source is from fossil fuels. So this is the way we are categorizing the hydrogen production methods. The hydrogen production methods can be categorized by using the source of the feedstock, then the type of the feedstock, and the process implemented for this generation of hydrogen. There are different methods and different techniques to generate hydrogen, and in that there are different methods based on the thermodynamics. Like if you are giving the energy or taking out the energy to generate this hydrogen, that is one method. And if you are using a catalyst to generate to generate the hydrogen or to make this reaction happen, there are two types of reactions, that will be a catalytic reaction and the non-catalytic reaction. And the other one to categorize this hydrogen production method is the oxidants. Like if you are generating the hydrogen in the using the method where the oxygen is used and it is not used, so it is called the oxidant method and the non-oxidant method. So based upon these three important things and the source of feedstock available, we are categorizing this hydrogen process. In this, if you are able to generate hydrogen using the natural gas, oil, and coal as a feed, then these are called fossil fuels. If you are able to generate hydrogen by using biomass and water as a feed, then it is called renewable energy as a source. So using fossil fuels and natural gas, we can generate hydrogen from steam reforming, that is also called as steam methane reforming, and the partial oxidation, autothermal reforming, decomposition, combined reforming, dry reforming, plasma reforming, steam iron process. So if you are able to generate hydrogen using this coal, then you can go with the thermochemical process where the energy can be given or taken. That can be gasification process, pyrolysis process, or direct combustion. These are all fossil fuels for generating hydrogen, which in turn generate the carbon dioxide also. So if you go with the renewable energy sources, there are two feedstocks available, that is biomass and water. So if you are able to generate hydrogen using this biomass from the renewable energy source, you can use for fermentation process, biophotolysis process, metabolic process. And completely, if you want to generate hydrogen without generating any carbon, we will directly use water electrolysis process and photolysis, thermolysis. These are the available process based on the feedstock and the source of the feedstock available. So as I mentioned, the type of hydrogen color, here is the hydrogen color wheel. And if you see, if we compare this hydrogen color wheel from earlier to now, the hydrogen color wheel is going to increase. As we are very much interested in the green hydrogen, we can start with green hydrogen. So the green color of a hydrogen indicates that if you are generating hydrogen using a water electrolysis, along with the renewable source of electricity. That means you are using renewable source of electricity to split the water into hydrogen and oxygen, then the generated hydrogen is called green hydrogen. And if you are using any renewable energy such as solar power, wind power, that can be green hydrogen. And if you are restricting only specifically to the solar power to split this water into hydrogen and oxygen, then this is called yellow hydrogen. And if you are using any nuclear power, that can be used to split hydrogen to water from water and oxygen, then that can be called as a red, pink, or purple color. So if you are, for example, if you are using a nuclear power plant to generate the electricity, and that generated electricity from the nuclear power plant is used to split the water, then it is called pink hydrogen. Then if you are using direct nuclear power to split the hydrogen, then it is called red hydrogen. And the other main hydrogen generation methods are SMR method, which is called a gray hydrogen. In this steam methane reforming, you will generate hydrogen from methane, which is giving out as a carbon as a byproduct. So this is called a gray hydrogen. In gray hydrogen, the CO2 emissions are more, which the carbon is released to the atmosphere. So this is called a gray hydrogen. If you are able to store that carbon generated from the steam methane reforming, then that is called a blue hydrogen. I think there is some disturbance. I think there is some disturbance. Can anyone mute?
Sir, we are trying to mute.
Okay. Yeah, thank you. So I'll continue from the gray hydrogen. Like if you are generating the hydrogen using a steam methane reforming process, and you are the natural gas as a input feed, and you are generating hydrogen along with carbon dioxide. The carbon dioxide is a byproduct. You are releasing into the atmosphere, causing the greenhouse gases. So this will be called gray hydrogen. The blue hydrogen means if you are generating this hydrogen and carbon dioxide as a byproduct, if you are able to store that carbon dioxide, capture that carbon dioxide, and sequestrate it, then it is called blue hydrogen. So as I mentioned in the thermochemical gasification and pyrolysis method, where the feedstock is being heated, in that case, if you are using oxygen and or a pyrolysis method to heat the feedstock and generate the syngas and purify the hydrogen from that, then it is called a turquoise hydrogen. And traditionally in many industries, hydrogen is being generated from the coal. So if you are generating the hydrogen from directly coal, then it is called a black hydrogen. And if you are generating hydrogen from a lignite coal, then it is called brown hydrogen. So I think I think now you can understand what is the hydrogen color spectrum. And if you see here, the white hydrogen is the hydrogen which is normally available in the earth. So we have studied about the hydrogen color spectrum and the different hydrogen production sources, and we know that during production of hydrogen, the carbon is emitted. So here there is a comparison that what is the energy consumption, hydrogen yield, and emissions while generating hydrogen. So if you see the feedstock, I have taken natural gas, oil products, coal, and water as the feedstocks. So if I'm taking if I want to generate hydrogen using natural gas, the 1 mole of hydrogen requires 42 kilojoules of energy. And if you are giving 1 mole of feed, it can generate 4 mole of H2 by using natural gas as a feed. If you are generating 4 moles of H2, giving 1 mole feed of natural gas, you are generating 10 tons of CO2 per 1 ton of H2. Like if you are generating 1 ton of H2, giving natural gas as a feedstock, you are generating 10 tons of CO2. So this is a major comparison. And if we have already seen that the major hydrogen production is done using natural gas. So here the carbon dioxide releasing to the atmosphere is high. So here we are shifting towards carbon neutral environments, so that we are preferring the water electrolysis technologies. So in this, if you see for the oil products, the energy consumption is 50 kilojoule per mole. So to generate hydrogen, we require 50 kilojoule per mole of energy for a oil product as a feedstock. And 1 mole of oil product as a feed, we are able to generate 2.7 mole of H2. And if you are generating 1 ton of H2 using oil products, you are releasing 12 tons of CO2, which is more high than the natural gas. And if you see the coal, using coal, if you are producing hydrogen, the energy consumption is 60 kilojoule per mole. So, and you are having 22.3 mole of H2 you are releasing for 1 coal mole of feedstock. Then 19 tons of CO2 you are releasing for 1 ton of H2 production using this coal. And if you compare all these are all the fossil source of fuels. And now if you see the water, which is a renewable energy source, you are using 245 kilojoule per mole. This is the energy consumption to split the water into hydrogen and oxygen, and you are able to generate 1 mole of H2 per this 1 mole of feed. Now, if you see here in the emission column, the blue line is completely zero. That means where this hydrogen generation using water electrolysis doesn't give any CO2 emissions. So we are preferring water electrolysis as a major hydrogen production method in the present future. And along with this, if you see all the fossil fuels using natural gas, oil products, coal, we are able to generate hydrogen, and along with that many byproducts which may be or may not be useful. But if you are using water electrolysis and generating hydrogen, we are generating oxygen compared to the hydrogen in many stages. Like if you are able to generate 1 kg of hydrogen, we are generating more kg of oxygen, that which also makes this environmental pure. So this is here an added advantage for this water electrolyzer. As I mentioned, there are different hydrogen production methods based on fossil fuels and renewable energy sources. So in fossil fuels, we have seen the hydrocarbon reforming. That is called the reforming, in which can be categorized as steam methane reforming and partial oxidation and autothermal reforming. Earlier, I have mentioned many production technologies in these fossil fuels, but in that all are the hydrogen production methods, but these three are majorly used in the industries, having some significant importance. And if you see the renewable energy sources, the hydrogen can be produced from biomass process, which is consists of biological process and thermochemical process, along with that water splitting process. So green hydrogen we have highlighted here because we are looking for green hydrogen generation methods, which is used through the water electrolysis process by employing renewable electricity. So the reason it is called green, because there is no emission of CO2 and there is no emission of greenhouse gases. So this is the reason we are calling this as a green hydrogen, and we are using the renewable energy for this generation of hydrogen. If you see here water splitting process, there are different water splitting processes such as thermolysis, photolysis, and electrolysis. In this electrolysis, this thermolysis and photolysis are a very early stage process which the yield of hydrogen is not up to the mark. So we are using electrolysis process for generation of hydrogen, which is widely known to all of us. So there are different electrolysis process in that some of. Yes, sir. Are you able to see my screen, sir?
Yes, sir. You can proceed, sir.
Okay. So here we have seen different hydrogen production methods. From here, we'll go into detail of each and every method. Just on a briefly, I'll explain all these methods. If you are able to generate hydrogen using fossil fuels, we have seen the steam methane reforming. In steam methane reforming, there is a methane reactor, water gas shift reactor, and H2 purification. So here, the hydrogen is generated from methane. Methane is reacted along with steam, that is water, at the methane reactor stage, where you can see the equation CH4 plus H2O gives rise to 3H2 plus CO. Here the generated hydrogen is collected and sent for the purification, and the CO is going to the water gas shift reactor, where either some more hydrogen is being generated along with the water, and the CO2 is given as a byproduct. So the generated hydrogen also goes to the H2 purification for the purification. So this is a basic introduction of a steam methane reforming. Whether if you see this process, there is a pre-treatment of the feed, that is hydro desulfurization will be done, and all the impurities from this methane is removed before sending it to the reactor. and the pre-processing of this hydrogen will methane will be done before sending into the methane reactor. And after generating the hydrogen, post-processing work is also done for the purification of the hydrogen to meet the end application requirements. So if you see the partial oxidation method, this partial oxidation method is a catalytic is of two types. It is a catalytic method and non-catalytic method. We can use the catalytic and non-catalytic also for generation of hydrogen using this partial oxidation method. In this partial oxidation method, it is similar to the steam methane reforming, but here only oxygen is being induced into the reactor, but not the steam. So the methane coming here is desulfurized, then the carbon components are removed, and it is going to the partial oxidation reactor, where this methane is being reacted with oxygen and forming hydrogen and CO. This formed hydrogen is sent to the gas treatment. Here, partial oxidation is done at if you are going for a non-catalytic reactor, it takes around 600 to 700 degrees centigrade of temperature, and it occurs at 50 to 60 bar of pressure. And if you go for a catalytic reactor, it takes to 600 to 900 degrees centigrade, and for a non-catalytic reactor, it goes around 1200 to 1500 degrees centigrade. Then, if you see the next is a autothermal reforming. This autothermal reforming is a process that uses the steam methane reforming and partial oxidation process to generate hydrogen. So here, some amount of oxygen and some amount of steam is being added in the reactor along with the methane to produce the hydrogen. This is a most effective compared to the partial oxidation and steam methane reforming. But steam methane reforming is extensively available and currently using in the industries. This is a biological hydrogen production process where there are different biological production processes such as fermentation, biophotolysis, and bioelectrochemical system. In this fermentation process, there is of dark fermentation and photofermentation. This dark fermentation and photofermentation, all this biological hydrogen production are done using organisms or the bacteria. There are different bacteria responsible for the generation of hydrogen. In this dark fermentation, the feed is being fermented, and mesophiles and thermophiles use this forms this hydrogen in that feed. And if we go for a photofermentation, there is a two different organisms, sulfur organisms and non-sulfur organisms, which form the hydrogen. In this direct biophotolysis, algae and the cyanobacteria are used to form the hydrogen. This direct photolysis is directly the light energy is used to split the hydrogen into hydrogen and oxygen. In the indirect photolysis, the same bacteria is used, but this hydrogen and oxygen is not split directly, but carbon is formed. Then again, from this, the hydrogen is being generated. Then if you see the microbial electrolysis cell, here exoelectrogens are the organisms which cause the feed to generate hydrogen. But this biological hydrogen production process have low production, and they doesn't mean the requirement. So these are not used widely. They are under experimental stage. So here the hydrogen production is done using the organisms. So exact metabolism of the organisms and the production is not clear. So we doesn't use this biological hydrogen production much. And here, if you see, the light energy is required to generate this hydrogen, which means artificial photosynthesis is required, and which is very expensive. So there is one of the backdrop that why we are not using this biological hydrogen production. And if the hydrogen needs will be very much high, and if you are able to generate this hydrogen from these methods, it cannot meet the requirement, because the hydrogen generated here cannot be taken properly, and there will be of more losses. And the generated hydrogen here is difficult to store, because this hydrogen is need to be collected in a proper way. And now if you see the thermochemical methods, there are two types of thermochemical methods. That is a thermochemical gasification and thermochemical pyrolysis. So these two methods use the same feedstock, which will generate the syngas. And from that, the syngas, the hydrogen along with other components will be present, but the hydrogen is being separated using different separation technologies. So in the gasification method, it takes at high temperatures, that is more than 700 degrees centigrade. Here it converts this organic or fossil based fuels into carbonaceous materials. Now in this gasification and pyrolysis, in the gasification mostly we are the most change is we are adding oxygen or steam for this reaction to happen. So we are adding the oxygen and steam and giving this feed, leaving carbon monoxide and hydrogen as an end products. So these generated hydrogen, carbon monoxide, carbon dioxide will need to be separated or absorbed in different reactions to generate this hydrogen output. In pyrolysis, the pyrolysis is same kind of gasification, but it is done in the absence of oxygen. Where in the gasification, a controlled amount of oxygen is injected into the reactor, but in pyrolysis, this reaction takes place in the absence of oxygen. And the pyrolysis, as there was no oxygen, the pyrolysis will take place at 1400 degrees centigrade. So if you are using this pyrolysis and if you are able to generate hydrogen, giving methane as a feed, then this is called turquoise hydrogen. Here we can see the typical flow diagram of a gasification process. This is one of the example I have shown here for the clear understanding of the gasification process. There is a thermalizer which the feed is being present. In this thermalizer, we are introducing the feed from this hopper. So this is the reformer where this feed is being present. Like this, we are giving the feed. At here, it consists of two jackets, that is an inner jacket and this is an outer jacket. So from here, the feed goes in here. We are raising this temperature to 700 degree, above 700 degrees centigrade, and we are adding some process steam and gas of H2 and N2. The gas is being added here, H2, and from here the feed goes here, and the gasification is done at this place, and thermogas is released. So this released thermogas, along with leaving ash and tar as byproduct. But this process is intended to reduce or remove the tar formation, because which gives us the more efficiency. From here, the feed is being the thermogas is being taken to this reformer. So taken to this gas reformer. Before that gas reformer, we are again injecting some more amount of H2O so that the concentration of the hydrogen will be increased. From the reformer, from 700 degrees centigrade to it goes to up to 400 degrees centigrade for the reforming stage. From the at this reformer, the thermogas is being converted to syngas. From the syngas, it is going to the same. From the syngas, it is going to the same reformer for heating application, and the earlier feed was coming in the inner jacket, and this syngas was coming to the outer jacket for heating of this feed initially. So from here the syngas goes to the waste heat recovery boiler, which reduces the heat, and from there it goes to the gas scrubbers. From there it goes to the gas scrubbers, and from here it goes to the water gas shift reactors. From here, water gas shift reactor, then again it goes to the CO2 separation. In this CO2 separation, the CO is carbon dioxide is separated from the syngas, and and the hydrogen is being sent to this hydrogen separation stage. And from here, hydrogen is being separated using pressure swing adsorption method. Then the pure hydrogen is being taken to the hydrogen storage. And here, if you see the feed we are giving at this place, and we are able to generate the hydrogen and storing the pure hydrogen of 99.99%. But in between, we are generating the carbon also, and this carbon is separated at this stage, and it is stored in the solid form. This is a solid carbonate storage. So here we are not causing any environmental impact on greenhouse gases. So this is a typical block flow diagram of a thermochemical gasification method. And if you see for the water splitting technologies, there is a thermolysis method of generating hydrogen, which due to the increase of the temperature, that is for till 1400 degrees centigrade, we are able to generate hydrogen. So H2O, and we are supplying the heat to this water, and we are generating this hydrogen and some O2. And photolysis, here photocatalysts are used to transmit visible light. So the light source is being transmitted on this hydrogen to generate this hydrogen and oxygen. Now here comes the electrolysis procedure for generation of hydrogen. So we all know that electrolysis is the process of decomposition of water into hydrogen and oxygen when the electric current is passed through the water. So there, if you know in the basic form, the electrolyzer consists of a cathode, a negative charge, and anode, a positive charge. So if you see the very basic experiment of hydrogen, that we all know that we take a beaker, we pour some water and keep two rods of called as electrodes, and we supply some electric power. So we think that the water will be split into hydrogen and oxygen, but it doesn't happen because the water itself cannot split into hydrogen and oxygen, and the water needs to be either acidic or basic to split into hydrogen and oxygen. So we are making this water into acidic nature or basic nature. So this is a basic experiment which we are performing in a very lower level for the splitting of water. And this is the main principle of water electrolysis, which is intended to further refined for the effective hydrogen and oxygen collection from the water. So, and if you see the very entire cell, it consists of two electrodes, that is the cathode and anode, a closing member called, we call it as a beaker, and an electrolyte or a water. So if you pour the water, then the water electrolysis will not happen. But if you make that water into either acidic or basic, then the water electrolysis will happen. So we are calling that solution as an electrolyte. So to generate hydrogen from the water, we need water, which is mixed with electrolyte. So we can call it as an electrolyte. Then a negative charge, that will be a cathode, and a positive charge, that will be an anode. So these are the basic components required for doing this experiment. But if you are able to generate hydrogen by doing this experiment, you cannot collect it properly. So now if we restart this experiment, providing electrolyte water, you see that some bubbles are being formed at both the electrodes, at the bottom of both the electrodes. So then these bubbles will appear to the top of the beaker, and if you see, this is the electrolysis process. We can see that hydrogen and oxygen is being generated, but we could not collect it. So then the next approach came as a gap cell. So what the experiment has done is, we want to separate this cathode and anode so that the generated oxygen and hydrogen will be separately collected. So we place a diaphragm, a membrane between these two electrodes, that will be separating this hydrogen and oxygen generated at the electrodes. So this is called a gap cell. From the basics of the beaker experiment, we moved on to the gap cell, where this hydrogen and oxygen is being generated. And here the formation of the hydrogen and oxygen is there, but the effective utilization of this cell is not seen. So from that, we made this electrolyte, we made this gap cell to a zero gap cell, so that there will be no space between both the electrodes, that is cathode and anode, along the membrane. So in the zero gap cell, the cathode, membrane, and anode, these three are combined at each place, and the electrolyte is poured. So here we can see some efficient results, that if you see in the zero gap cell, this is the beaker, and this can be a membrane, and this anode and cathode is being developed like this, so that there is no gap, which increases the efficiency of this gas generation, and making easy of the collection of this gas generation. So from there, this electrolyte has been made, this membrane, the separation membrane, has been furthermore made into a diaphragm membrane, which is already being used in this alkaline electrolyzers. So this diaphragm membrane separates these two electrodes, making it more efficient. So as I have mentioned, water is required for the generation of hydrogen. Ideally we require 9 liters of water for 1 kg of hydrogen generation. But considering all the losses, we require 11 liters of water, nearly 11 liters of water to generate 1 kg of hydrogen. And the energy consumption, because we need to provide the electric energy to split this water into hydrogen and oxygen, we require 39.4 kilowatt of watt hour per 1 kg of hydrogen generation. But considering the different losses like ohmic losses, activation over potential losses, and other transportation, mass transportation losses, the actual energy required will be varying from 50 to 56 kilowatt hour per kg of H2, and this may increase more based on the different electrolyzer technologies. Due to their inefficiencies and due to their advancements, also this value will be interchangeable. And the water treatment, if we see, the water need to be as per the ACM type 2, the required water for the hydrogen should have resistivity more than, so the water should consist of total organic carbon of 50 ppb and less than 5 of sodium and chloride content. So this is the type of water required for the hydrogen production. And here if you see, to produce these specifications of water, normal water need to be purified, and this purification also requires some energy consumption. And this consumption of energy will be impacting on total cost of the hydrogen generation. So to treat the normal water, 0.001 kilowatt hour per liter of brackish water is required, and for treating seawater, 0.0046 kilowatt hour per liter is required. So the energy required for a demineralized water treatment is 0.0016 kilowatt hour per 1 liter. Purifying, we can also use the seawater also, but if we use the seawater, this seawater consists of different materials, not like a regular water. So this may corrode the electrode or this impacts the electrode, and the electrode will tends to degrade, which will reduce the life of the electrolyzer, and which may impact the output purity of the electrolyzer. But different experiments are going on to use the seawater in the electrolyzers. So using seawater in the electrolyzers may reduce the overall cost, but reduce the overall cost along with the reduction of the life of the stack. As I mentioned, there are different types of electrolyzers, in which one is an alkaline electrolyzer. The alkaline electrolyzer is different from other electrolyzers because it is an old existing technology. There are different alkaline electrolyzers presently working in different areas in India. So in the alkaline electrolyzer, the electrolyte used is an aqueous solution. That is, the water is containing either NaOH or KOH with a typical concentration of 20 to 40%. The electrolyzers which we are using, which means the alkaline electrolyzers which we are using, is having the water along with KOH and NaOH with these different compositions varying from 20 to 40%. If you see this alkaline electrolyzer, there is a cathode, diaphragm, and anode. And here, if you see the anode reaction in this alkaline electrolyzer, the hydrogen is being generated at a cathode. So we are sending water to this cathode electrode. That cathode electrode materials are nickel and carbon platinum. So these are the some of the type of materials used for the cathode. And here, if you see at the cathode, we are sending 1 unit of water along with some electric power. So this is being separated into hydrogen and 2 OH minus. So this OH is being transferred from cathode side to anode side by this diaphragm membrane. So from this diaphragm membrane, here at the cathode side, the water is giving us input and hydrogen is being generated, and this oxides OH is being transferred from cathode side to the anode side. At this anode side, this transferred electron is coming in contact with this anode side. Here, these electrons, electrons will mix and make H2O and half O2. So if you see the overall cell reaction, H2O is giving H2 and half O2. So to balance this one, you can go with 2 H2O gives to H2 and O2. Neglecting this half, you can go with H2 and O2. and here 2H2. So the electrolyte used here is, as I mentioned, it is a potassium hydroxide, KOH, or sodium hydroxide, NaOH. The working temperature of this alkaline electrolyzer is 60 to 80 degrees centigrade. So if you go for a solid oxide electrolyzer is a high temperature electrolyzer. It is categorized as a high temperature electrolyzer because it uses steam as an input and works at 500 to 850 degrees centigrade. So here in the solid oxide electrolyzer, the reaction starts at the cathode as mentioned in the alkaline electrolyzer. So you can see H2O plus 2E minus gives to H2O and O2 minus, and this O2 is being transferred from cathode to anode. Wherein the alkaline electrolyzer, OH minus is being transferred from cathode to anode, but here O2 is being transferred from cathode to anode. Where this O2 is combined, O2 is reacted to form oxygen. So the anode materials here are LSM, that is lanthanum strontium manganite, and cathode are nickel doped yttrium stable manganese. So these are the materials used. As this is a high temperature electrolyzer, the silicon materials is mostly preferred for this electrolyzer to resist with the temperature. And the membrane here is used is yttria stabilized zirconia membrane. So yttria stabilized zirconia membrane will allow the oxides to move from cathode to anode. And coming to the PEM water electrolyzer, PEM electrolyzer is called as a proton exchange membrane electrolyzer or solid polymer electrolyte membrane electrolyzer. In this PEM electrolyzer, there is no requirement of adding any potassium or sodium electrolyte into the water. And in the PEM electrolyzer, at the anode, the water is being sent to this anode. Here, water is being split into protons and oxygen is being generated. The 2 electrons is being released and it is transferred from anode to the cathode. In this, the electrons are being traveled from anode to cathode, and the generated protons at anode side is being transferred from anode to cathode through this PFSM membrane. That is a PEM, that is called proton exchange membrane. From this, the protons are migrated from anode to the cathode. Here in the cathode, these protons which come from this anode side and along with these electrons both mix and form hydrogen. And if you see the overall cell reaction, water gives rise to H2 and half O2. So if you see this, the reaction is being like this: 2H2, and I'm going to balance this reaction. It is 2H2, and there is no half, and it becomes O2. So if you see this membrane is of different kinds. As I mentioned, I will go deep into this PEM water electrolyzer, the working principle, the materials, the construction of this PEM electrolyzer, and the BOP, which includes the balance of plant for this efficient working of a PEM electrolyzer. The membrane here used is a solid electrolyte membrane, that may be Nippon, Fimapen, and other companies are there which provide these membranes. This is a typical comparison between the PEM electrolyzer and the alkaline electrolyzer. As alkaline electrolyzer is an existing technology, we can see that there are more advancements in this alkaline electrolyzer which give high efficiency compared to the PEM electrolyzer. Alkaline electrolyzers take more time for the initial start, and PEM electrolyzers take very less time for the initial start. If you go for any large production of hydrogen, then we go with alkaline electrolyzers, and for a small and intermediate capacities, PEM electrolyzer is preferred. If you see for the cell temperature, PEM electrolytes operate at 50 to 80 degrees centigrade, and alkaline electrolyzers operates at 60 to 80 degrees centigrade. This is the normal operating temperatures which are commercially available, and beyond this also the electrolyzers may operate, but which are in the laboratory or in the experimental stage. So if you see the rated production 0.265 to 30 nm cube per hour, the PEM hydrogen is PEM electrolysis being used for this production capacity, and in alkaline it is 1 to 760 nm per hour. But if we see this one, the electrolysis has been now increased to more, and the production capacity has been increased very much. The rated power is 1.8 to 1.74. So to generate 1 nm cube or 1 kg of hydrogen, the required kilowatt power is given here, and these are not the updated one. The ranges have been very much reduced. So this is the specific energy consumption in the PEM electrolyzer. If you see 5.8 to 7.3 kilowatt hour is required to generate 1 nm cube of gas. And in alkaline electrolyzer, it is the energy consumption of 4.5 to 7.5 kilowatt hour per 1 nm cube of gas generation using alkaline electrolyzer. So the other operating conditions are the maximum pressure of a PEM electrolyzer is 7.9 to 85 bar, and for alkaline electrolyzers it is up to 30 bar. It is limited to only 30 bar. And if you see the hydrogen purity in PEM electrolyzer and alkaline electrolyzer, both are mostly same by using external purification units. And the system cost is comparing to the PEM electrolyzer, alkaline electrolyzers are very less cost because of using their normally available materials. In the PEM electrolyzer, we use the noble metal as a catalyst, which is of high cost, and the life of the metals and the catalysts are very less compared to the alkaline electrolyzers. So this is the construction of a PEM electrolyzer. The PEM electrolyzer consists of bipolar plates, gas diffusion layer, and a membrane electrode assembly. In this, as I mentioned this equation, at the anode side, hydrogen is being fed into this electrolyzer. From there, at the anode side, water is being fed into this electrode, and here the water is being coming out, where the protons H plus is migrating from anode side to the cathode side. So there is a DC power supply. From here the electrons are traveling this side, and these electrons combined with protons to generate hydrogen at the cathode side. To make this phenomena happen, it requires different parts called as cell components for the efficient generation of hydrogen and the efficient collection of generated hydrogen. So these are the different parts as I mentioned here. The water is coming at this area. It is going through a bipolar plate where it consists of a flow channel, from where it is having some space and time for the reaction with this catalyst at the anode. Then the generated oxygen is being taken out from this bipolar plate. The protons migrate from here to this side, to the cathode side, and it consists of another bipolar plate where the generated hydrogen is being taken out from here. These are the materials used for the PEM electrolyzer. So as I mentioned, noble platinum materials are used for hydrogen evolution at the hydrogen side, and oxygen side likewise. So the hydrogen generation at the hydrogen side and cathode side is called as hydrogen evolution reaction, and at the anode side it is called as oxygen evolution reaction. Platinum, iridium, ruthenium are some of the materials used for oxidation evolution reaction at the anode. So these are the noble catalyst materials. And if you see at the cathode side, platinum, platinum black, carbon platinum are used for this hydrogen evolution reaction at the cathode side. Now if you see, there is a membrane in between this anode and cathode which allows only the proton. So this membrane is called a polymer alkylate membrane, or which is coming from Nippon, Fimipen, Flemion, and other companies. So these are providing these PFSM membranes. So these PFSM membranes are perfluorosulfonic acid membranes, which allows only protons from anode side to the cathode side. And the other components which I have mentioned are bipolar plates, and gas diffusion layers and are the current collectors. So titanium is used as a material for the bipolar plates, and the metallic carbon paper is used as a gas diffusion layer at the cathode side, and metallic gas diffusion layer is used at the anode side. So this is the membrane electrode assembly, which consists of a membrane, anode, and cathode either side of the membrane. As I explained about the membrane, now what is the proton exchange membrane requirements is the proton exchange membrane should have high protonic conductivity for the transport of ions. So it should be able to transfer protons from one side to other side, that is from anode side to the cathode side. And this is the major requirement as it is a proton exchange membrane. And the other is high oxidative stability. The membrane should have high oxidative stability so that it doesn't allow any oxygen generated from the anode side to the cathode side. So this will impact the purity of the generated hydrogen. And next, coming to the membrane, it should be mechanically and thermally stable, because in any conditions the membrane should not degrade mechanically or thermally. So it should resist for all the mechanical and thermal conditions. And if you see, the membrane should have low permeability of gases. The membrane should not allow any gases to pass through it, so that it may see that the oxygen and hydrogen which are generated cannot mix at this place. And it should be electrically insulated to prevent any short circuits at the cell. The ionomer used for this membrane should be mechanically and chemically stable to withstand these harsh conditions. To bind this material, the ionomer must be stable. And if you see the commercially available and the supported membranes for PEM electrolyzers are, as I mentioned, there is a PFSA membrane, that is perfluorosulfonic acid membranes. Which are some of the Nippon membrane, Fimopen membrane, Aciplex membrane, and these are some of the membranes of PFSA which are used widely in the PEM electrolyzers. These membranes have high strength and high efficiency. And if you see the bipolar plates, these are also called as cell separators, which is having a fluid flow channel on either side. These channels allow the water to pass to the cell, which makes some time for the water to react with the electrodes on the either side of the membrane. So the requirements of the bipolar plates will be, it should have high bulk electrical conductivity, and the bipolar plate will have either side of two gases, that is H2 and O2 compartments, because for the bipolar plate, one side the hydrogen will be there and the other side the oxygen will be present. It should facilitate for the efficient movement of the water in these channels, and it should perform a gas evacuation. Means the generated gas during the starting of this process, it should efficiently send the water from the source to the anode or the cathode, whichever is required. And if you see, this bipolar plate is common for all the electrolyzers, not only for the PEM electrolyzers. So if you are using this bipolar plate and sending water from the flow channel, it should efficiently send the water to the electrode for the reaction. And after the gas is being generated, it should efficiently bring back the gases to the out. Means the gases need to be evacuated. And it should be highly electrical conductive, and it should have high surface conductivity. And the materials chosen for this bipolar plates should be hydrogen embrittlement, where because the hydrogen is being present at this surface of these materials, and it should be in stable in oxidizing environment. The selection of this membrane should be very much cost impactive, which should give less cost, which may reduce the overall cost of the electrolyzer, thus indicates the levelized cost of hydrogen will be low. And these are the gas diffusion layers, also called as current collectors, which they are placed on the anode side and both the cathode side also, because these will diffuse the generated gas at the surface of the electrodes, and it will take out this gas from the electrode to the bipolar plate. So major gas diffusion layers being used in PEM electrolyzers are porous, sintered, titanium gas diffusion layers are being used, because for the efficient movement of this hydrogen, oxygen and the water between the bipolar plates and the electrodes. So if you see, it is a electrolyzer stack which consists of, if you can see, this is one cell and this is another cell and this is one cell. Here it is a combination of 3 cells are there, and this is the membrane, this is a anode and this is a cathode. If you see, we are providing the water at the anode side here, and here at the anode the reaction is being takes place and the oxygen is being generated. The generated oxygen is being taken out. So from here the generated oxygen is being taken out from here. As we see, our reaction H2O so here oxygen is being generated, and 4 electrons also being generated. This generated oxygen need to be taken out. So this is the reaction taking place at this area. So from here, these protons are being traveled from this side to this side, that is from anode side to the cathode side. Here it reacts with this electrons passing this side. Passing this side, the hydrogen is being generated. So here if you see in this bipolar plate, this side the water is being supplied, and here the hydrogen is being supplied. And this side we are providing again water. Means if you see, this bipolar plate consists of either side, it is this side as a hydrogen and this side water is being supplied at this bipolar plate. This image represents that the efficient working, and to make clear that either side of a bipolar plates. If you are going to stack a cell, means if you are able to generate some amount of energy from one cell and you want to generate more energy, we make different cells and stack them. So this is called as a electrolyzer stack. So the generated hydrogen from each cell is being collected. For example, if you are able to generate some 0.5 kg of hydrogen from one cell, for an example, and if you are going to generate a same cell, if you are keeping another 0.5 kg and here 3 cells are there, it means 1.5 kg of hydrogen you can generate from total this stack. So this is called stacking, and bipolar plate is very much useful for the stacking of the cell. Earlier unipolar plates are used for the electrolyzers, where only one side the channel was being provided. In this, if you are providing only one side the flow channel, then you cannot stack the cell. So if you want a higher production of capacity, then you need to keep number of cells, and you need to supply the water and electric power separately to each cell, which makes the electrolyzer will be very much big, and it occupies more space, and which will have more losses. So the stacking of the cells has been made using this bipolar plate. This is the 3D image of a stack arrangement. So here we see the water is being sent at this bipolar plate. You can see here the flow channels of this bipolar plate. Here this is the anode. At this anode, the water is being reacted with this material, and here oxygen and some unreacted hydrogen also is being coming. So every electrolyzer will have some conversion rate, which will convert which will convert the water into hydrogen and oxygen. So if you are sending a unit of 10 liters of water, as per this conversion factor, the 10 liters of water will not be converted into hydrogen or oxygen. Only some amount will be converted into hydrogen and oxygen, and the other water will be recirculating. That is the reason we are showing here water input and taking out the oxygen and water. This oxygen is being coming from the reacted water, and this unreacted water is coming as a water outside. So from here, the protons is moving from anode to the cathode side along with some electrons. Then here these electrons and protons combine and form hydrogen. Here we can see only the protons have been moved from this side, from anode side to the cathode side. But here output we have seen the H2 and H2O also. So that is, here it says that hydrogen and water also is present. So this is we need to understand that the system is having some loss, that water also being transferred from this side to the cathode side. So these are some of the losses which will be explained in the next slide, that each electrolyzer is having what are the losses of the electrolyzer consists. So this is a two cell stack. This is one cell and this is the other cell. This is the water and gas crossover. This is used to illustrate the example of a effective current collector. See, this is the bipolar plate, this is the current collector, and this is the membrane. Here, the electrodes are being present, and the reaction is being taking place here at this side. Here we are introducing the water and taking out this oxygen, and from here the protons are moving, and here the hydrogen is being generated. If you see this image, and if you see, as I mentioned, that there are some impurities in this in this working of this electrolyzer. These are the water and gas crossovers. So here, if you see that there is a movement of water from oxygen side to the hydrogen side, that is from anode side to the cathode side, and there is some traces of oxygen is present in the generated hydrogen due to the movement of oxygen from anode side to the cathode side. These are called the mass transfer losses. So for the working of this cell, there are different losses, that is the mass transfer loss and the ohmic losses are also present, because we are supplying the electricity for the splitting of this hydrogen into this water into hydrogen and oxygen. There are some losses in the power also. So if you see, in the initial stage we are sending water and we are generating oxygen, and hydrogen we are collecting here. And if you see in the next stage, some water also being transferred to this cathode side. This is called water drag. And if you see, due to the diffusion, oxygen is moving from anode side to the cathode side. So here, like this, at the generated hydrogen also, there are different impurities due to these mass transfer losses. If you see this PEM electrolyzer, this is a basic process flow diagram which explains how this entire system will work. So till now we have understood about this electrolyzer stack. So we have seen what are the components present in this electrolyzer stack, and we have seen how these components are how these components are sourced, and on what basis these components are being selected, and how they are attacked, and how we are sending this water, and what is the movement of this water and hydrogen and oxygen at this stack. Now we are seeing the total integrated system which is required for the efficient running of the stack, that it consists of a water gas management system, then hydrogen collection and purification system, oxygen collection and purification system, along with some other utilities and an input power system. So if you see, our feed is a water, as this is a water electrolyzer technology. From this water, it is going to the water feed pump. The initial water purification is done, then it is sent to the water gas separator. this is a two-phase liquid and gas separator, where the gas and liquid is being separated. From here, the water is taken to the heat exchanger to maintain the required temperature for this working of this electrolyzer. Then it is going to the ion exchanger to remove the further impurities in the water. Then it is going to the electrolyzer. So we have sent the water. Now, as per our reaction, the hydrogen and oxygen are need to be generated. The generated hydrogen will be at the cathode side, and the generated oxygen will be at the anode side. So the oxygen along with some unreacted water is being collected at this gas water separator. The unreacted water will be recirculated to this stack, and the oxygen collected here will be sent to this demister for further cleaning and being released outside. So we have got our oxygen, and now at the cathode side the hydrogen is being generated and some water is being also transferred to the cathode side. Here it consists of hydrogen and water. From here the hydrogen and water is being separated. The separated hydrogen is being recirculated. As this is a basic process flow diagram, the line has been shown like this, but it is being recirculated in this manner. And now the gas is being separated at this. It is of a hydrogen gas consisting of some other impurities such as some amount of hydrogen, some amount of water, and oxygen. So here there is a condensate trap. This is the condensate trap to remove the moisture from the hydrogen, and from there it is taken to the buffer storage. So here initially the generated hydrogen is being stored, and for the further purification, to get the required purity output, it is sent to the deoxidizer, where this hydrogen consisting of water, that is H2O, and oxygen. Here this hydrogen and here the oxygen present in this hydrogen is being reacted and being converted into water. So here H2 plus O2 goes to H2O, and the end products of this deoxidizer will be hydrogen and water. This water is sent to this dryer system, which the water is being separated from the hydrogen, and the final hydrogen is being produced. So here we can obtain pure hydrogen. So in this webinar, we have seen about what are the different hydrogen production methods, what are the different applications of hydrogen, where it is being widely used, and different production methods based on different sources of feedstock. And we have seen about the water electrolyzer technologies, where hydrogen is being generated without any production of carbon dioxide. And we have studied about the working and construction of a PEM electrolyzer, and balance of plant for the PEM electrolyzer. So so we know that there are many options for considering hydrogen as a very good fuel, and because we need to know the hydrogen storage is a critical issue, and we need to implement some more methods for the effective storage and transportation of hydrogen. So from this generation, we can store this hydrogen and can be transported for our other purposes. Thank you.
Thank you, Harshvardhan sir, for your wonderful presentation.
Yes, sir.
Sir, for 30 seconds, please switch on video for AICTE upload portal.
Yes, sir. Sure.
Dear participants, please switch on video for 30 seconds only. Later we are having a query session. I'm requesting all the participants, please switch on video.
Vinod sir. Vinod Kumar sir.
Yes, sir. Yes, sir.
Thank you very much, sir, for Chandra sir,
Sir.
please take a snapshot.
Yes, sir. I'm taking. Already taken, sir.
Okay, is it over?
Yes, sir. Yes, sir.
Now we'll go to the question answer session. Doubts clarification by resource person.
Any queries from the participants? Please unmute your audio. Any queries from the participants?
Hello.
Yes, sir.
Hello. Good evening, sir.
Yes, sir.
Thanks for this wonderful lecture. I have one query, that is, how can green hydrogen compete economically with fossil fuels and other renewable sources of energy in the short term?
Sir, can you come again? That it is not clear.
How can green hydrogen compete economically with fossil fuels and other renewable sources of energy in the short term?
Sir, in the short term, if green energy need to be give competence to the other of generational method using fossil fuels, it is not only directly using the generated hydrogen, but it needs to be used in other byproducts also, like using the hydrogen for the generation of e-methanol, or using the hydrogen for the generation of ammonia, which this byproducts also need the demand and increase of the utilization of these byproducts increases along with the regular hydrogen production, then it can compete with other other fossil fuels. And coming to the economics, as of now, there is a limited usage in these water electrolyzer technologies for the green hydrogen. The cost of this one is increasing, but many of the OEMs and PSUs are coming forward and should come forward to make generate this hydrogen using this water splitting technologies, which will be which will generate this hydrogen more, and the utilization of this hydrogen will increase more. So thus the cost will be reduced, and choosing the good feedstock available at the local, which does not impact any cost issues on the bringing of the feedstock into this production technology or the production place, will also reduce the cost of this green hydrogen production.
Thank you very much, sir. Sir, one more query I have. How
Yes,
can
sir.
government, private sectors balance investment in green hydrogen technology with the other renewable energy priorities?
Yes, sir. Government is very much encouraging and investing in green hydrogen technology, sir. There are green hydrogen refilling station also is being built at different locations in India, like which we are directly working on in one of the green hydrogen refilling station at NTPC Noida, where the hydrogen is being generated on site using the alkaline electrolyzer. They are storing it, compressing and storing it, and dispensing to the fuel cell buses. So there are the production of the fuel cell buses are increasing, the hydrogen generation stations are increasing, which will make this hydrogen being as a large production from water electrolysis compared to the fossil fuels. So like this, they are government is making this PSUs to PSCs to generate this hydrogen, sir, which will may future increase to more and reduce the cost. And government also is keeping the new hydrogen policies, which will make other parties also to generate the hydrogen. They are giving subsidies in SECI, the Solar Energy Corporation India is giving the hydrogen tenders also they are giving. They are supporting the companies who are working on the hydrogen in stage wages. So recently the stage 2 also has been released, and some of the Indian companies has been already selected and they are working on hydrogen technology with the support of our government.
Thank you very much, sir. Thank you very much.
Yes, hope you are clear.
Any other queries from the participants?
Hello. Hello.
Yes, sir.
Sir, am I audible?
Yes, you are audible, sir.
Sir, this is Saravanan from Tiruvannamalai, Tamil Nadu, India.
Yes, sir. Please go on.
My question is, we have studied the major source of hydrogen is sun. That is the gift of the nature.
Okay.
But the hydrogen what we are going to produce in the near future, whether it will be sustainable or not, the answer what I need either yes or no.
Sustainable means in what way, sir?
Sustainable in the sense it should be coping along with the integrants of the nature, sir.
Okay. So the hydrogen should be integrated along with the nature. That is not directly, sir. Not directly, yes, because the total demand using only with this generation is not sufficient.
Sir, may I take the answer as no or yes?
You can take as no, sir.
If the government spend a lot of money to develop this hydrogen energy, so is it not sustainable? Sustainable is a question, means why they give more money to that project, sir?
Sir, actually the intention is not only to generate hydrogen, sir. We are generating only hydrogen because it is having some high value comparing to all the fuels, and it will not generate any carbon. So which will in turn will reduce the greenhouse gases. So make this environment as a carbon neutral and having high energy value. There is only the hydrogen is the source. So all are looking for the hydrogen in India and abroad also, and our government is focusing on hydrogen for this reason.
Sir, one more doubt, sir. That hydrogen we get it from that seawater.
Yes,
so
sir.
then it's okay. If we are going to get that normal water, means so already we have water scarcity, sir. So that is also one more problem. How we rectify it? If get this hydrogen from seawater, so is it feasible? So that also the question, sir.
Yes, sir. Actually, this is one of the major concern we can say, sir. So this is the reason we are not we are telling directly no for the sustainability of the hydrogen, because the water should be purified water, and many tests and experiments are going on for the seawater also. So surely in near future we will be getting a seawater electrolyzer, and because the seawater electrolyzers are already available but not commercially available, they are under the laboratory scale. One of my friend is from the Chennai itself, and he is working on the seawater electrolyzer. So this will soonly come into picture, but not very near. So this takes some time, but when this seawater electrolyzer comes into the picture, the hydrogen will be definitely it will be sustainable.
Okay, thank you, sir.
Thank you.
Hello, sir.
Yes, sir.
If I want to establish small setup for hydrogen production in our laboratory, example 5 kg production of hydrogen by using alkaline electrolysis, how much cost it involved, sir, for small scale?
Sir, actually 5 kg production is not a small one at this means at this college one, sir. So 5 kg is somewhat a medium capacity, which is also not big. But to generate 5 kg of electrolyzer directly, we cannot say that this much of money is needed, sir, because there are different components and different technologies available. So if you are going with alkaline technology and as per different locations and different parameters will make this to decide the cost of the electrolyzer, sir. So we need to work on that, and if required, we will definitely work on that and come back to you to show you that what is the cost of the cost required for setting up a plant at your college premises, and we can calculate the ROI also for that one. And if you are keeping a hydrogen plant, it should be, we need to calculate the levelized cost of hydrogen, sir. So total how much hydrogen you are generating, and after generating the hydrogen 5 kg you are mentioning, this may be the 1 day capacity generation or per hour capacity generation. The details we need to get to know, sir. So after generation this hydrogen 5 kg, if say you are generating per hour 5 kg, then you will, if you are operating for 10 hours, you are generating 50 kg of hydrogen at your college premises. So this requires more land area. This requires the regulatory body approvals. And after getting all these, this 5 kg of 50 kg of hydrogen per day, where you want to store, sir, you need for a storage cylinders. Then after that, what will be your end application for you are generating this hydrogen and you are storing this hydrogen? Till how much you can store, sir? You need to use it for any application. So is there any nearby applications that you can sell or give your hydrogen? So I think as right now there is nothing at your college premises. So at this moment, generating of this much amount of hydrogen or generating amount hydrogen is not good. This is the what immediate answer we can give on this one, sir. But if you have a definite application of using this hydrogen, or if you want to showcase in the laboratory a purpose that we are able to generate hydrogen, we can go with very nominal small capacities that we can help to set up at your college, sir.
Okay, sir. Thank you. So on behalf of Mechanical Engineering Department, Lakhireddy Baledi College of Engineering, I extend my sincere thanks to Vinod Kumar sir, Harshavardhan sir for insightful detailed presentation on hydrogen and its applications and challenges. Harshavardhan sir mainly focused on why hydrogen, the characteristics of hydrogen, supply demand of hydrogen, different ways to generate hydrogen, and based on the color also SAR addressed, and the yield of hydrogen based on fuel source used. SAR also critically explained the types of water electrolyzers like alkaline electrolysis, solid oxide cell electrolyzer, and PM water electrolysis. Once again, thank you so much, Harshavardhan sir, for your enlightened lecture.
Thank you, sir. Thank you. You're welcome. Thank you for providing this opportunity, sir.
Thank you very much, sir.
Thank you, sir.
Thank you, sir.
Sir, thank you, sir. If it is completed, can I leave, sir?
Yes, sir. Yes, sir.
Thank you. Thank you. Thank you, participants, for joining and attending my webinar. Thank you for joining.